Welcome back. So the next example we're going to have a look at, very, very common. We've got a square sheet of tin, and the tin overall measures 12 by 12. Okay, so it's a square sheet. This little example here, we've cut the corners out because what we're going to do is we're going to fold those edges up and create a tray or a box, depending on how shallow or deep it is. Okay, so we're starting out with 12 by 12 sheet of tin metal. Okay, sheet metal. 4 equal squares of edge x centimetres are cut out of the corners. So these are squares that are cut out, and the side length of these little squares is x. Okay, and we're going to turn the sides up to form a rectangular box. Okay, so what we want to do is find the values for x for which the volume is 100 centimetres cubed. Okay, now this is, I mentioned in the last video, in this course in assessments, you'll be given the rule for volume. But in this one, we're going to work it out, okay, from scratch. So how do we go about this? We've got 12 by 12 with a bit cut out of it, okay. How many lots of X has been cut out of that side there? Have a think. How many lots of X has been cut out? You've got one there. You've got one there. So you've got 2 lots of X cut out of 12 centimetres. And this is what I'm talking about, making expressions that describe the context of the question. This is very, very common, this question. You'll see it guaranteed popping up. Okay, so let's have a look. The values for x for which the volume is 100 centimetres cubed. Well, if I'm working on volume, then I need a rule that describes the volume of this potential box for all possible values of x. Okay, so let's work out a rule for volume. So part A. Part A, determine the rule for volume. Okay, so we know that from the last question and from all the other years of maths that you've done, length times width times height gives you volume, doesn't it? Okay, so here we'll have, let's see, if I turn this box up, turn these sides up to create the tray or the box, how high will they be? What's that dimension there? What do you think? So I'll turn these 4 flaps up, 4 tabs, turn them upwards. What would the height be? It's going to be x, isn't it? Because we've been given that's a square. So when we turn it up, that's going to be x units high. However big that cutout is, x represents the height. Okay, so we've got times x. It's going to be our height. We need an expression for width. So we start with 12 centimetres, and we've had x removed. So it's in fact 12 less 2 lots of x. Okay, it's been reduced by 2x. So what would an expression be if something's been reduced? You're going to add, subtract, multiply, or divide. I hear you say you'd subtract. You're going to subtract 2x from 12. So the expression in terms of x for the side length is going to be, width is going to be 12 minus 2x. Okay, and similarly, the length is going to be 12 minus 2x. Can you see how that works? So you got length was 12, whatever x is, it's going to be 2 lots of x taken away from that 12, whatever we cut out here. Okay, the more we cut out, the taller the box is going to be and the smaller the base is going to be. So we've got 12 minus 2x times 12 minus 2x times x. So that is x 12 minus 2x all squared. Okay, so that's a rule for the volume of this box, whatever the value of x is going to be. Okay. So the values for x for which the volume is 100. Okay, well, what we're going to do now then is we're going to let volume, so this is part A still, so we're going to let V equal 100. Now I'm going to show you a couple of ways of doing this. I'm going to show you how to do it algebraically, and I'm going to show you how to do it using your graphing calculator as well. Okay. So we'll set it up 100. So volume equals 100 equals x 12 minus 2x all squared. Okay, it's a perfect square. Actually, what I think I will do, this would be a graphing calculator type question. I think we'll just do it using the graphing calculator, and I'll show you how to do it. It's actually quite straightforward. Okay, so 100 equals x times 12 minus 2x squared. And what we'll do first of all, I'll just get my graphing calculator working so I can show you the steps through with the graphing calculator. So using CAS, now here's the steps, I'll summarize. So using CAS, so my calculator starting up is using all my memory, so this is lagging. Give it a chance to start up. Okay. So when we're graphing these, we'll go home, choose graph, and the volume is x outside of 12 minus 2x all squared okay, and bring that. We've got to put multiply, we've got to go multiply in there. Try that. Okay, there it is there. Now, you can see it's right off the screen. Okay, so what we've got to do is we've got to adjust our window. And this is really important, and I've talked to you about this before. We need to adjust the window so I can see the whole graph. Okay, so what we'll do is we'll go menu, window zoom, and window settings. Okay, and you'll see that the x values are okay. We can see from 0 to where it hits 0 again. So it's a similar sort of graph to the last one. We're going to restrict the domain in a sec. Okay, 0 to 0. But it's the height that's the issue, the y values. Okay, so if we go menu, window zoom, window settings, and we want to make that y max much, much higher. Okay, so let's make it, let's try 500. You might have to have a couple of goes at this to get it right. Try 500. There you go, you can see it. So I might try 300. Menu, window zoom, window settings. Let's try 300. So we got a decent sized graph. Okay. So there it is there. Now I can, with your little touchpad here, you can hold that down on the blank space a couple of seconds and you can drag your graph around so you can see it. Okay. So there's your graph, and it's similar to the last one, only it's a positive graph rather than a negative graph. Now, let's think about the domain. The actual values that would be applicable to this particular question. Okay. Just need to get my graphing calculator back up. We've got, that's our rule, and we want to work out what are the valid values of x so that we've got a box. Okay. Now, if x increased to halfway along, which is 6, there it is there, then there'd be no base, would there? So if I cut out big cutouts like that, there'd be 4 of them that were 6 by 6 centimetres, then the box would cease to exist. You just end up with 4 squares of metal, no box. Okay, so the upper value of x is going to be 6 centimetres. Okay, so let's jot that down. So domain, so restricted domain. So x such that it's going to go up to 6. Okay, and the other end, the value of x that we wouldn't have a box would be if I didn't cut anything out at all. I just have a flat sheet. Okay, so 0 would be the lower end of your domain. Okay, so if you didn't cut any corners out, you wouldn't have any box, you'd have a flat sheet. If you cut 6, you'd be cutting 4 smaller flat sheets and you still wouldn't have a box. Does that make sense? So you'd be going from values of 0 up to 6. That would be your domain. Okay, so we have a look back here. That point there represents the volume. Remember, this is volume. This is the value of x that you're cutting out. Volume is represented as 0 at the origin. It goes up to a maximum, which we'll calculate shortly. It goes back down again to 0 at this point here, okay, which is 1, 2, 3, 4, 5, 6, which is just what we worked out. Okay, so what we can do now is we can click on that, double click, and we get our rule back. And what I'm excuse me, what we're going to do is we're going to put our domain in. Okay, and to do that, what we do is we go Control equals, put a little vertical line in, and then we need to write it. We did this when we did quadratics. This is from 0 to 6 inclusive. So it's 0 less than or equal to, because it's got the square brackets, x less than or equal to 6. Okay, so 0 less than or equal to x less than or equal to 6. Okay, enter. And that cuts our graph. It goes from 0 to 6. Okay, so the next bit says find the maximum volume. Okay, well, where's the maximum volume? Oh, sorry, no, the first bit we need to work out the values of x where the volume is 100 centimeters cubed. Okay, to do that, what we do is we create another graph over the top of this one. And what we do is we create a graph that represents the volume, this measure here, equaling 100. Okay, so what we're going to do is we're going to draw a horizontal line straight across where v equals 100. And where it cuts this graph will represent the x values where the volume is 100. Okay, so to do that second graph, what you do is you hit tab, and then it's simply equals 100. So this is f2 of x represents the y axis, and the y axis is volume. This is volume equals 100. Return, and there you have a line that represents the volume equals 100. Okay, now we've looked at this before where we've got intercepts between graphs, and you might remember it's analyze graph. So we're going to go menu, analyze, intersection, and so it says lower bound down in the bottom left hand. You put your vertical line on the left, click, drag across, and then click again. So we've got a value of 100. And then again, we go Menu, Analyze Graph, Intersection, click to the left, drag, click to the right. And we have a value of 3.21, 100. So the values of x for which the volume is 100 would be 1 centimetre. Okay, so if I cut a square out 1 centimetre by 1 centimetre out of here, and out of here, 1 centimetre by 1 centimetre, and folded it all up, then I would have a volume of 100 cubic centimetres. If I went along 3.21 along here and 3.21 and cut out those squares and folded it up, I would also have a volume of 100 cubic centimetres. Okay, so one would be wide and shallow, and the other one would be taller and narrow. Okay, but they both give you 100 cubic centimetres. Okay, so let's look at the maximum volume, part B. The maximum is going to be, as we looked in the last example, the very uppermost point of the graph. So we're measuring volume vertically. So the biggest height of the graph, the maximum of the graph, is going to be the maximum volume. Okay, and the maximum volume, we go Menu, Analyze Graph for a maximum, and then we choose. See, it says graph. We have to choose which graph because we've got two graphs. We're going to choose that one. Click on the cubic graph, and we go lower bound, click, upper bound, click, and we can see that the maximum volume for this scenario would be 128 cubic centimetres, and that would occur if we cut little squares out that were 2 by 2 out of each corner, 2 centimetre by 2 centimetre squares, and folded it up, we get a maximum volume of 128 cubic centimetres. Okay, so it's a very, very common problem that you'll come across is the box problems. Alrighty, so just recapping, at x equals 0, we've got 0 volume. At x equals 6, we've got 0 volume. Okay, we have, if you want to work out a particular volume, you draw a second graph as a horizontal line at that value, and then you analyse the intercepts. The y coordinate is the volume, the x coordinate is the amount that we're cutting out of the corners. And to work out a maximum, then we select the correct graph and we analyse graph for maximum. Okay? So I've got one more video to go to you in this series, and thank you guys.